Euler is king. Repeat after me. Euler is king.
Euler is king.
There you go. When it comes to mathematics, Euler is king. He is the most prolific mathematician ever. Paul Erdős is a modern, was a modern mathematician who came pretty close. But what do I mean by the most prolific? He had the sickest dance moves of all the mathematicians. No, he published more original work, okay, than any other mathematician before or since, right? And he had a great sense of humor. He did a lot of times they did math by candlelight, and he lost the sight in his eye. If you see pictures of Euler, he's squinting when he's older, and he actually, after he went blind in one eye, he actually produced more work, more consequential work than what he had when he had two eyes. And they asked him, there you go. They asked him, Euler, how were you able to do that? And Euler said, well, what was the point? Yeah, I was less distracted. Right? I only had one eye instead of two eyes, right? Brilliant, funny, sums up Euler. Euler is king, okay? So what we're learning right now is Euler's method. A lot of things are named after Euler's. Euler's identity, which is kind of what we talk about at the end of the year. This is what I showed you. It was on the math club shirt long ago. If I ever got a tattoo, this would be the one I got backwards on my forehead so they can read it in the rearview mirror when I'm driving, but I haven't gotten the courage yet, or the permission, really. But yeah, that's Euler's identity. So Euler is king. But what we're going to do now is we're going to use the power of lines to help us approximate function values where we don't know what the actual function is. Now, we did this already back in 3.7. Remember, we did linearization, and that was basically find the equation of the tangent line. And then once you had the equation of the tangent line, you could plug in values to the left or right of the center of the approximation, which was the point of tangency. And that gave us a way to approximate a function. Okay, so let me insert a page just to review it. I hope my battery power stays. All right, so let's review what we did in linearization. Okay, linearization. Look at that in cursive. Boom. So that, let's say I have a function. We'll just make it in blue here, like that. And I want to approximate a value, but I really don't know much about the curve other than I have a point and I know how fast it changes. I have a differential equation. So we can call this point right here that I know, we'll call it x equals c for the center of our approximation. Now, if I could find the equation of a tangent line there, like that, let me extend that out. Boom. Now remember, in the vicinity of our center, which would be a little bit to the left, a little bit to the right, the function value of the line L of x is a decent approximation for the function value f of x, right? That's the whole idea behind it. At the center, it's the same value, right? At that point of tangency, the function f and the equation L of x, they share the same y value on the same slope. But after that, they vary, right? And it's only good within like a certain radius. We could say go plus r and minus r. If you go too far away from that center, I mean, you could see the disparity between the two curves, right? But in the neighborhood of the red value is a decent approximation of the blue value. Now, once we had that value, there was also a way to determine if our approximate value in red was too big or too small, over or under approximated it, right? What would we use for that comparison or for that analysis? The concavity, right? If we could determine the concavity of our function f of x in between the interval from our center to whatever value we're approximating, the concavity of the original function will tell us if our linear approximation is too big or too small. In this case, it would be too what? Too big, because f of x is concave down from c to whatever. And it could also be from the left, like from negative whatever to c. All right, so let's go ahead and say that we were trying to approximate now. I'll use the darker blue. Let's say we're trying to approximate this value here. Okay, I'll call this x equals a. So the whole idea then is this value here, L of a is approximately, or I'm sorry, we got that. Let's do it the other way around. We'll say that f of a, the actual function value, is approximated by L of a. Okay. Well, that's not bad at all. That's not bad at all. But here's what Euler's method is. Euler's method takes advantage of the simplicity of a line. And Euler says, hey, if we're going from C to A, it's not necessary to take one giant step from C to A. He was of the opinion, what if I did this, and just bear with me for a while, what if I divided that region into two? Let's call this B, right? What if then I walked out on the tangent line up to B, okay? But since I have the derivative equation, what if now at B, I recalculate the slope, which then would give me a tangent line maybe like this, right? And now, what if I walked out along that tangent line to A? In other words, what if I broke it up into two steps? I thought that color would contrast a little bit better. It doesn't. So let's do this. Okay. So instead of stepping all the way out, what if I step out and then I recalculate and then I step again? Now, you can see that the purple now is going to be a little bit closer to the blue, isn't it? Because we just learned slope fields. Everywhere I calculate a slope in this vicinity, it's going to follow the same trend of the curve. Well, why do it in 3 steps or 2 steps when I could do it in 3? So what if now I just, or 4, let's divide each of these. Okay, so let's call this A, B, C, let's call this D, and let's call this E. I know, this is kind of just for theoretical purposes. If you get the idea, you're good. All right, so now I'm going to step out on that original tangent line to here. And now I'm going to recalculate the slope, which might be this, right? And now I'm going to walk out on that tangent line to here. And then I'm going to recalculate the slope, which might be that. And then I walk out on that tangent line. And then finally, I recalculate the slope there. And then I walk out along that tangent line. Yeah. You see what's happening? I'm just walking out on different planks. And each time that new plank out upon which I am walking, is that what I would say it, is closer and closer to the curve. So it should give me a better approximation, right? And now 4 intervals was kind of arbitrary. Do you see a limiting process here? I mean, in theory, what if I took 100 different steps or 1,000 different steps? Each time I'm recalculating the slope. The slopes are going to be hugging the curve better and better and better the more subintervals I use. Yeah, and you could actually program this. This is like the genesis of a program that can allow you to approximate function values in the vicinity of a known value and knowing the rate equation. Okay, so that's the idea behind Euler's method. We're going to learn Taylor polynomials at the end of the year, which is kind of used for the same purpose. But a Taylor polynomial would say, hey, instead of using a line, let me draw that again, just to kind of set you up for the end of the year. What if I had the same predicament, right? Here's x equals c. Oops, I didn't do that well. Haste makes waste. There you go. All right, so here's x equals c. When we study Taylor polynomials, instead of like going out on linear bridges, we're going to say, hey, a linear function does a decent job in approximating what I'm trying to approximate. But you know what? A quadratic might actually be better. So if I could find the equation of the quadratic, maybe it's a parabola that opens down, right? Maybe this could be like, we'll call this L sub 1 or L sub 2. The line would be L sub 1, this would be L sub 2. And then you're like, hey, well, if a quadratic does a nifty job of it, maybe a 4th degree polynomial would be even better, right? So maybe it would actually hug the curve a little bit more or something like that. We'll call this L sub 3. So you could tell that back in the day, people were trying to approximate actual function values in the neighborhood of a given point and a rate equation, right? Now, what's nice about the Taylor polynomials is it will, if the more and more terms you use, sometimes it actually becomes the curve. And polynomials are much easier to evaluate than, let's say, the original curve was a sine of x curve, right? That's really hard. In fact, your calculators, I think we came to this conclusion, your calculators are programmed using these Taylor polynomials. If you typed in like sine of 7.6, it's going to plug it into a polynomial that represents sine of x in that vicinity up to however many decimal points we need. Now, for humans, polynomials is not as desirable because the powers get larger and larger, right? And if I have to raise a number like 3.46 to like the 8th or 9th power, and then it's going to be real tedious. Enter Euler's method again. Euler's like, yeah, you could do all that fancy polynomial jazz, but why not just keep it linear, man, and just break it into smaller and smaller steps? Okay. They both accomplish the same thing. All right, so that's what Euler's method is. Elvis is the king of rock and roll, I guess. But who's the king in the math world? Euler. Leonard Euler. Lenny Euler. Okay. If you memorize this chart, which I'm hoping you will, it makes using Euler's method so easy. Okay. Memorize the headings in the chart. All right. Now, you're not going to see any kind of chart on an AP exam, okay, because they actually do the computations using what we did in 3.7. They find the equation of a line, then they plug it in, and then they find another equation of a line, and they plug it in. This is what I came up with to systematize the process. All right. Let me show you what I mean. Example 1. Hey, we're already on example 1. Can you believe that? If I stop the recorder now, what would I call it? Example 0 or prelude? Euler's king. There you go. All right, here we go. Example 1. Ready? Given the differential equation, dy dx equals x minus 2. Okay. It's in terms of the independent variable and an initial condition, y of 0 equals 5. Find an approximation for y of 0.8 using Euler's method with 2 equal steps. Okay, and it's typically going to say show your work. Oh, you're drawing a crown on Euler. So you will be commanded to use Euler's method when you're expected to use Euler's method. There's not going to be like some subtle wording like there was for the sect equation. It's increasing at a rate that's proportional to itself. No, it's going to say use Euler's method. And that is how we pronounce it, by the way, not Euler. Yeah. Back in the day in Houston, they called their math club the Houston Oilers, and they spelt it like that. Yeah. Okay. You're either going to be given the number of steps you're required to take, or you're going to be given the width of each step. Okay. You're also going to be given your target. Okay. No. It's going to be tedious. Now, a lot of the times these are done without a calculator. If you could do it for 2 or 3 steps, you could do it for 200 or 300 steps. It's just more and more tedious. All right, so here's what we have to do. We have to first figure out what our delta x is. Okay, delta x is b minus a over n. Where have we seen that? Everywhere. Yeah, that's the width. So where am I starting? I have the point 0.05, right? So my starting x value is x equals 0, right? Everyone see that? And I want to end at x equals what? 0.8. So I'm going from left to right. Would you agree? Because Euler's method works from right to left as well. I'm starting at x equals 0, which is my center of approximation. That's my point of tangency. And I only want to know what it is 0.8 of a unit away. All right. So instead of using a single tangent line, writing the equation of the tangent line, and then plugging in a 0.8, which would be taking one big step, we just want to take how many steps? 2. We want to break it in half. All right. So once you find your delta x, which let's do that, we're going from 0 to 0.8. So that's going to be 0.8 minus 0, b minus a, all over how many steps? 2. So each step is 0.4. Oh, that makes sense, right? Yeah, 2 equal steps. Now we can make our chart, our table, okay? So let's look what's in the chart here. You're going to start with your x and y column. That's going to be your seeding value. And when we say it's an initial value, it doesn't have to correspond with x equals 0. It's just, again, some ordered pair that satisfies the original function. Naturally, then, we're going to calculate the slope there. And what are we going to do with the slope? We're going to figure out then, if I walk out along that line on that slope by that delta x 0.4, how much is my y changing from the previous? So this is a very important column. I want to figure out delta y. How do I figure out delta y? It's the slope m from the previous column times delta x, which we already found. Where does that come from? Well, it comes from algebra 1, right? Slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which is this. Multiply both sides by delta x and you get delta y. Once you figure out how much that y value has changed as you step out along there, what do you y? You add that back to the old y value, right, from the previous column, and now you have your new ordered pair. Now you're standing at a new point, right? So again, here's what we're doing. I see a tangent line there. I'm going to walk out along it at 0.4, and when I do, I'm going to see what my elevation change was, right? And then I'm going to add that elevation change back to the previous y value to get at the current y value. And then I see a different line, and I walk out along it, 0.4, calculate the elevation change, add it, so on and so forth, right? All right. So if you memorize this chart, all that does is it makes the calculations and organization a lot easier. So let's go ahead and do that. That's my next step. All right, move those over here. So like the next step center, right? Yeah, okay. X, Y, what comes next? Don't say Z, slope, okay? I want the slope, you can call it M, or you can call it dy dx, whatever. And once I have the slope, what am I going to do? Yeah, that's the delta y. That's the money step. I know delta x in this case is 0.4, but how much did the y change? And of course, you could write the formula there if you want. It's m dx. And then I'm going to get my new y value, y sub nu. Okay. And then we bring that back around to the next row and we proceed. Okay. Let me show you. If you memorize these column headings, Euler's method is fun easy. All right. But it is a little tedious. We got decimals. So we might have to go ahead and use our workbench, which is okie dokie. All right. So let's put our initial condition or initial value in there. 0, 5, right? Everyone go with that? All right. Now, what is the slope of the tangent line at the point 0.05? Well, plug it in here. Well, it's a function of x. So what do I got to plug in x equals 0? I get -2, right? The slope is -2. But I'm not going out a full unit. I'm only going out a fourth of a unit horizontally. So now I got to figure out if I walk out along a slope of -2, how far down am I going? So delta y is m times delta x. What's our delta x? 0.4, right? We calculate that first, 0.4. All right. So what's 0.4? And you can do this off to the side. What's 0.4 times our slope of -2? -0.8, right? So that's -0.8. See that? So if the slope of the line is -2, if I walked out 1 full unit to the right, I'm going to go down 2 full units, right? That's what rise over run means. But I'm not going out a full unit of x. I'm only going out 0.4 of an x. So instead of going down 2 units, I'm only going down 0.8 of a unit, right? All right, now I add that back to the previous y value. So 5 plus -0.8 or 5 minus 0.8 is what? 4.2. 420. All right. Yeah. Now, what do we do with that value? Now we get our ordered pair. Where are we standing? Well, you're going to add delta x. What 0 plus 0.4? 0.4. So there's my new x value. And then I just bring the other value around, 4.2. All right. So again, all I did is I walked out along that tangent line slope, 0.4 of a unit, and I lost 0.8 of a y value. And now I'm going to go ahead and recalculate. Now we proceed the same way. How do I find the slope? Now that I'm using this point, well, it's still x minus 2. What is 0.4 minus 2? Negative 1.6, okay? So notice now the slope is a little bit less steep, right? The slope actually increased even though it's less steep because it's less negative. Now what do I do with that? Off to my side of my workbench, I take the slope now, negative 1.6, and I multiply it by what? Oh, did I put D? Yeah, that should be delta x, my bad. In the column, right, delta x. So it's negative 1.6 times 0.4. Oh my gosh, I need to, how do I do this? Well, let's do old stack multiplication. Because a lot of times these are without calculators, right? So you don't want to mess it up. That's 6. And then I know it's negative, and then I count decimals. 0.64? Is that good? Yeah, okay, good. Yeah. So negative 0.64. I didn't go down as much. Is that right, Zachariah?
Is that right? No,
It was 4 times.
Is that really right? Okay, 4.4 times negative 1.6. So
6 times 4 is 24.
I see.
And then
Right,
4
okay.
times 1 is 4 plus 2 is 6. And then we count
So the
count
decimal
decimals.
comes
Yeah.
out two.
Yeah, we have 2.
Yeah.
So 1, 2.
See, I
Yeah.
was thinking 6.4.
This is why Euler's method is easy, but it's tedious. Because a lot of times you don't have a calculator. But this is why Euler came up with this method. Because as tedious as it is, it's a lot easier than using polynomials of larger degrees. Okay. In fact, tangent line approximation, what we did before, is Euler's method with one step. Okay. So if you'd rather do linearization with this column heading, you're just doing one step and you're there. All right, we're almost got our new point. What do I do now? I take the 4.2, which was my current y value, and now I'm going to subtract 0.64. Ay caramba. Well, we better put that 0 there. What are we giving to $4.20 minus 64 cents? $3 and what? 56 cents. Oh, I don't know. Look how fun this is. 4.20 minus 0.64. We got to line up the decimals now, right? And so we're going to borrow. Sorry, 2, we got to borrow, and that's a 6. And then 6, nope, now we got to borrow. Boom. So we get a 5, and we get a 3, and then, yeah, 3.56. Well done, Hank. Well done. Okay. Now, let's do one more. Let's add 0.4. What's 0.4 plus 0.4? 0.8. And then I bring that point around, 3.56. Do I proceed again? No. Okay, once you do your second step, look at this. This is why I like to rewrite it. You don't go again, that would be 3 steps. I did 2 columns, that's 2 steps. This is where I'm standing. I'm now standing at 0.8, 3.56. So what can we say? Can we just box that or highlight it? No. We now say so, and then we use terminology, approximation. So y of 0.8, what? Squiggles is approximately 3.56. There you go. No. Anytime it says approximate or estimate, you're on squiggle alert, squiggle alert. Anytime you have a fractional exponent between 0 and 1, you're on what? Cusp alert, cusp alert, cusp alert. He did that the other day. Yeah. There it is. That's Euler's method. Fun easy? All right. Let's keep going then. Part B. These make really good single sections in free responses. Okay. Part B. solve the differential equation, dy dx equals x minus 2 with the initial condition y of 0 equals 5, and then use your solution to find y of 0.8. So now we're going to be like, oh, why did I do the approximate value when I could have found the actual value all along? Well, there's more than one way to skin a cat, right? In the end, it's about getting that skin off that cat. Right? Amen. All right. And just press away. All right. What do you notice about this differential equation? It's a function of what? Just x. So these are the easy ones, right? We don't have to show the separation, but since we have that new skill, let's do it. dy equals, if I do x minus 2 dx, how's that looking on a free response?
Pretty good.
Not really, because I need parentheses around the x minus 2. Now, does that separate the variables? Yes, so that's a check. And then we integrate both sides. Sneak that slinky, slim, svelte integral symbol in there. What is the antiderivative of 1 really with respect to y? Y. Do we need plus c there? No, because it's going to come to the other side with ShamWow c. All right, x becomes what? 1/2x squared minus 2x plus c. Okay, so what do we know about this solution, general solution? It's a parabola that opens up, right? How am I going to find c? Plug in the initial condition. So over here, we'll say at 0.5 colon, and we plug it in. So we're going to get 5 equals 0 minus 0 plus c. You're going to get a check right there again for using your initial condition. All right. But that means c equals 5. So, right, summative statement, we plug it back into the same form. Once you solve for the general solution, c is super saturated, right? No more ShamWowing. So we get y equals 1/2 x squared minus dos x plus 5. Okay. And there's your particular solution. Why is it so particular? Yeah, because we found the value of c. Very good. We call it the particular solution, though, because it is the only one whose derivative is x minus 2 that happens to pass through the 0.05. No, that's why it's so particular. Yeah, very good. Now, what are we going to do with that? We're going to find y of 0.8. So it's not in function notation. So you could either say at x equals 0.8 colon, or you could just say y of 0.8. You can kind of use that notation on y like you would if it were f of x. And then you put equals. So let's see, that's 1/2 times 0.8 squared minus 2 times 0.8 plus 5. Now, if this were a free response question, would there be any incentive to go past this? No, we're done. But if this were a multiple choice question, or I'm sorry, a calculator question, and it could have been, if it were a calculator question, would you use your calculator up here to do the subtraction and the old retro multiplication?
Yes.
Probably so, right? The calculator only helps you with those intermediate calculations. So because we want to compare apples to apples, right, which can be a fun game, times 0.8, why am I typing it in? Minus 1.6, you do it, say plus 5, answer.
3.72.
Thank you for your help, 3.72. All right, that's the actual value. Yeah, what value did we find? 3.56, right? 3.56. Now, let's revisit linearization. Let's revisit linearization. Okay? If I didn't want to use Euler's method, this is kind of what the AB kids have to do. Approximate y equals 0.8 using the tangent line at 0. So what do we need for the equation of a tangent line? Point and the slope. Do we have the point? We do, it's the 0.05. So it's going to be 5 plus the slope times x minus 0. What is the slope there? Do we know what it is? No, but we could find it easily, right? dy dx is x minus 2. Plug in a 0, what do you get? Negative 2. So if you want to do it off to the side, dy dx at the 0.05, you write it like that, and it equals negative 2. So now I plug it in here. So it's really 5 minus. Now what did we do? Now we plugged in back in the day. Now we would say, so y of 0.8 is approximated by L of 0.8, which is 5 minus 2 times 0.8, which is going to be 5 minus 1.6, which is what? 3.4. Okay. 3.4, is that right? All right. Which is more accurate? 3.4, 3.56? 3.56. It's closer to the actual value than a one-step iteration. Okay. And so there you go. Euler's method in action. Now, here's one follow-up question. Instead of using concavity to determine if an approximation is over or under, since we have the approximation, can we use that when it's compared to the actual to infer what the concavity is? Yes, okay. Our approximation, whether it's a one-step or a two-step, it wasn't a waltz though, was it? No. It was a little smaller. It was a little smaller. So if our tangent line is an under approximation, then the curve has to be what? Concave up. Very good. Because here would be the tangent line, and here's what we found. Here's the actual. Here's the approximation. So now if you had to write that, here's what you would say. You would say since, what do we call it? Y, yeah. What did we call Euler's method? Anything? We didn't give it a name, but let's use L. Since L of 0.8 is less than y of 0.8, comma, the solution curve, which is y of x, okay, they didn't give it a name, is concave up on what interval? It's always going to be between the center of the approximation, the point of tangency, and the actual x value we're approximating at. Where was our center? 0, and we approximated at what value? 0.8. Yeah. So again, that's all you would write. 0.8 is to the right of 0. Yes, typically we do approximate to the right. That's kind of how we read. But we could have approximated easily to the left, and then just make sure when you write your interval, the smaller number goes first, right? So in the event, if we are approximating negative 0.8, you would put negative 0.8 to 0, okay? So there you go. That's a good little review. Okay, here's what I want y'all to do. I want you to do example 2, okay? And if you need a calculator for the intermediate yeah, I'm going to make you do 5 steps. Let's not do 5 steps. Forget that. Let's do 3 steps. Let's change it to 3 steps. Okay, do 3 steps. If you could do 3, you could do 5, right? But there's no reason to show off. All right, I'm going to do it as well, and y'all do it as well, and we can compare answers, okay? All right. All right, so okay, here's a gun. I'm going from x equals 2. Ruh-roh. What do you notice about the direction of our approximation? It's backwards. We're going from right to left. Ooh, okay. All right. So delta x must be what type of number? Negative, right? So yeah, your from is always your A, your to is always your B, right? In your interval, A to B, A to B. So delta x is going to be B minus A over N, right? Which is 1.5 take away 2 all over. Did it say how many steps? 3. I said 3. Okay, good. Boom. So let's see what that comes out to be. Yike, yike. Negative 0.5 over 3. That's not a fun. Let's do 5. It's easier. That's why I did that. See? Yeah. An ounce of prevention is worth a pound of cure. Okay. So let's do 5 steps. Más mejor que bueno. I don't know. Yeah. Oh, no, we'll just do this. We'll just do this, right? So negative 0.1. Okay, good. I just want to make sure we all have the same delta x. And now proceed. I will proceed also as well. Additionally, too. What'd you get, Hank? Let's go. Let's go. Giddy up, go, Daddy. Yes. Yeah. A lot of times. Calculator help you.